Hello everyone, my name is Vijay Rangod from HCA section. My room number is 2295180410, and this is my concept video of subject math, linear algebra and calculus. And my topic is about transforming vectors using matrices. One way to translate a vector in the coordinate plane is to multiply the vector by square matrix. To transform a vector using matrix multiplication, two conditions must be met. One, and the number of columns in the transformation matrix A must equal the number of rows in the vector column matrix V. How are matrices used in transformation? We can use matrices to translate our figure. If we want to translate the figure x plus 3 and y plus 2, we simply add 3 to each coordinate and 2 to each y. We simply add 3 to each x coordinate and 2 to each y coordinate. If we want to dilate a figure, we simply multiply each x coordinate and y coordinate with the scale factor we want to dilate with. What is transformation? Explain this different transformations with the help of matrix. Transformation means changing some graphics into something else by applying rules. We can have various types of transformations such as translation, scaling up or down, rotation, shearing, etc. When a transformation takes place on a 2D plane, it is called 2D transformation. How do you find transformations? The function translation or transformation rules are the below. F of x plus b shifts the function b units upward. F of x minus b shifts the function b units downward. F of x plus b shifts the function b units to the left. F of x minus b shifts the function b units to the right. Minus f of x reflects the function in the axis, that is upside down. What is a transformed vector? To transform a vector, we need to multiply the transformation matrix with that vector. This would result in a transformed vector, where the length or direction of the vector may be changed. What is transformation matrix in robotics? In robotics, the transformation matrix, the transformation matrix in robotics is found by multiplying the translation matrix by rotation matrix. By rotation matrix, we use homogeneous transformation as above to describe movement of a robot related to the world coordination frame. A homogeneous transformation matrix combines a translation and rotation into one matrix. Numeric representation 4 by 4 matrix. For example, a rotation of angle alpha around the y-axis and a translation of 4 units along the y-axis would be expressed as t form is equals to cos alpha 0 sin alpha 0 104 sin alpha 0 cos alpha 0001. And the in robotics applications, many different coordinate systems can be used to define where robots, sensors, and other objects are located. In general, the location of an object in 3D space can be specified by position and orientation. values. There are multiple possible representations for these values, some of which are specific to certain applications, transformations, sa- translation, and rotation or alternative. Translation and rotation are alternative terms for position and orientation robotic system. Toolbox supports supports representations that are commonly used in robotics and allows you to convert between them. You can transform between coordinate systems when you apply these representations to 3D points. These supported representations are detailed below with brief explanations of the usage and numeric equivalent in MATLAB. Each representation has an abbreviation for its name. This is used in the naming of arguments and conversion functions that are supported in this toolbox. At the end of this section, you can find out about the conversion functions that we are offered to convert between these representations. Robotic system toolbox assumes that positions and orientations in a right-handed Cartesian coordinate system. Next, what is standard matrix of transformation? The matrix in theorem Th Matlin is known as the standard matrix of the linear transformation. In theorem Th matrix of transformation. Every transformation induced by a matrix is linear. Theorem Th Matlin states that every linear transformation from into is induced by a matrix. The matrix is in theorem Th Matlin is known as the standard matrix of the linear transformation. Every linear transformation from into its induced by a matrix. The matrix in theorem Th, we show that every Th matrix strand of LTR 0010, we showed that transformation every transformation induced. Recall linear transformation of Rn as matrix transformation. Recall the transformations are linear. We now know that standard unit vectors map to the columns of matrix that induces the linear transformations. What we do not yet is that all linear transformations are induced by matrices to show that all linear transformations from Rn into Rm are matrix induced by matrices to show that all linear transformations from Rn into Rn are matrix transformations. We will demonstrate that the destination of the standard unit vectors under a linear transformation T determines the images of all vectors of Rn under T. We first illustrate this idea with an example. In general, every vector x of Rn can be written as a uniline unique linear combination of the standard unit vectors given to En. Therefore, the image of every vector x under an linear transformation T is uniquely determined by the images of E1 to En. Knowing T, E1, En allows us to construct a matrix A that induces the desired linear transformation. We formalize this idea in a theorem. Next, what does it mean to transform a vector? Next topic is about what what does it mean to transform a vector? A linear transformation is a function from one vector space to another that respects the underlying underlying uh, structure of each vector space. A linear transformation is also known as linear operator or map. We will To transform a vector, we need to multiply the transformation matrix with the vector. This would result in transform vector, where the length or direction or of the vector may be changed. We will take a look at the same questions which involve transforming vectors and then graph them to notice the changes between the normal vector and the transformed vector. Uh, To transform the vector, we need to multiply the transformation matrix with the vector. This would result in a transform vector where the length of direction of the vector may be changed. A scalar is defined a number of phi which transform to psi where psi is equal to psi. A vector is defined in an order triple of numbers. Transformation is a matrix that transforms one vector into another vector by process of matrix multiplication. The matrix that performs this rotation transformation between coordinate axes is called rotation matrix. Keep in mind that this matrix simply helps us express the components of the same vector in a different set of coordinate axes that have, in this case, been rotated counterclockwise around the z axis by an angle theta. Next topic is how, how matrices are used in real. They are used for plotting graphs, statistics, also to do scientific courses, sci- scientific scientific studies and research in almost different fields. Matrices can also be used to represent real world data like the population of people, infant mortality rate, etc. They are the best representation methods for plotting surveys. Application of matrices are not confined to mathematics. The concept is widely used in engineering, science, and complete applications as well. Matrices are the rectangular array of symbols or numbers that are set in columns and rows. There are a total of 9 types of matrices, and each of them are extremely important. Students get to learn about matrices from a basic level of class 9 or class 10. Understanding the uses of matrices in the initial stages will help them score higher marks in examination. Now, when it comes to uses of matrices in daily life, what are the real world applications of matrices? Students can find all the details here. In applications of matrices in real life, use of matrix in science or application of matrix in physics. Matrix or matrices are used in optic science to account for refraction and reflection. Matrices are also useful in electrical circuits and quantum physics. Moreover, matrices are used to solve AC network equations in electrical circuits. Uses of matrices in mathematics or application of matrices in statistics. Uses of matrices in maths include solving the linear equation. Matrices are incredibly useful concepts that occur in various applied areas. Uses of matrices in graphs. Digital images are referred to as matrices when used in graphic design. The rows and columns of the matrix are equivalent to the rows and columns of pixels. To put it on other way, next, encryption, games, especially 3D, economics, business, construction, dance, contra dance, animation, geology. Matrices are used for taking seismic surveys. There are types of matrices are there: column matrix, row matrix, null matrix, law matrix, diagonal matrix, upper triangular matrix, square matrix, symmetry matrix, and antisymmetry matrix. These are the applications of matrix. Thank you.